Thanks. I'm Matt Stevens. I'm a graduate student at UT, as Brandon said. I study galaxy evolution, similar to what Casey just talked about. And actually, we're collaborators, which means we have long, very interesting teleclons once a week. So that's fun. But I'm not here today to talk about galaxy evolution. I'm going to talk about quasars. As someone who did research on quasars as an undergrad, when I was talking to Raquel and she said that no one's given a talk on quasars, I thought that was just that was messed up. Someone's got to talk about quasars. So here I am. Okay, so quasars are super cool, and not cool as in like temperature. They are awesome, nifty, amazing. Aquazing, I just heard. And some of the reasons why are they're the brightest things in the universe, which is pretty cool. They were the first evidence. They were one of the first pieces of evidence to show that black holes truly exist. They have donuts, which I'll explain, and they're related to dragons, which is pretty neat. But most importantly, they are used as a tool by astronomers to study invisible matter between galaxies and gas in galaxies to answer important questions about the universe. So before we get into that, we've got to talk about the name, quasars. Quasar is short for quasi-stellar radio source. The radio part of the name comes from the fact that they were first discovered in radio surveys by radio telescopes like this. The stellar part comes from the fact that if you take an image in the optical, the quasars look like stars. Here's an image from Hubble. It has a quasar and a star, the two brightest things in the image. Raise your hand if you can tell by the shape which one's a quasar. Okay, we got one. You're wrong. You can't. So yeah, so quasars look like stars. When the astronomers saw this, they were like, are they stars? And it wasn't until they took spectra, optical spectra of the objects that they found out that they are different than stars. So if you don't know what a spectrum is, but you've seen one of these, you've seen a spectrum. A spectrum is a technique for splitting the light from a source into its different components. This is the sun spectrum that maybe you would see on a floor or a wall in your house. For quasars, you get a spectrum like this, where it's plotted as a line, where the y-axis shows you the intensity or brightness, and the x-axis shows you the wavelength or the color. And as you can see with the quasar spectrum, you have a very broad continuum that increases from the red side to the blue side in a power law shape. And on top of that, you have peaky features, which are broad emission lines. Now, if you compare that to typical stellar spectra, like you see on the left, you can tell that the right is very different than the objects on the left. So we have radio sources that kind of look like stars in optical imaging, but kind of don't look like stars in spectra, hence the name quasi-stellar radio source, or quasar for short. Now, another piece of evidence that astronomers found to show that quasars are not stars is actually the redshifted nature of the broad emission lines in the quasar spectrum. By the time quasars were discovered, Edwin Hubble had showed that there's a correlation between the redshift of broad emission lines in distant galaxy spectra with their distance. So quasars had redshifted lines that were redshifted similar to distant galaxies. So this showed that quasars are actually millions of light years away. Now, to be millions of light years away and still appear in the sky as bright as a star, this means that these quasars are extremely, extremely bright. So what is a quasar and why is it so bright? So this is just an artist's imagination view of what a quasar really looks like. you have a black hole at the center, and you have hot accreting gas material in a whirlpool swirling around onto the supermassive black hole. And this radiates at very high temperatures and glows very bright. So it's so bright that it can outshine the other stars in the galaxy. And as you know, galaxies have trillions of stars, so these objects can be a trillion times brighter than the sun. You can also see oftentimes they have a jet coming out of the center of the disk, and that has electrons being fired at near the speed of light. So they're very extreme objects. Based on their brightness, you might think their objects are quite large, but in fact they are the size of a solar system, of our solar system. If you were to bring a quasar to a nearby star that you see in the sky, say 30 light years away, this would be so bright that it would shine as bright as the sun does during the day. So let's zoom in and talk about how quasars emit their light. So they're bright because they're really hot, and they're really hot because they have a supermassive black hole at the center pulling gas into it. The way this works is, I don't get there. The way this works is the gas is swirling around the black hole, it's rubbing together, creating friction, which creates heat. This causes the objects to move closer to the black hole, where the gravitational potential energy turns into kinetic, which means the gas speeds up, and as it speeds up, it creates more friction, and more friction creates more heat. And as the gas moves, by the time it gets to this inner edge of the accretion disk near the black hole, the gas can be 1,000,000 degrees, and as we know from the Stefan-Boltzmann law, the luminosity or brightness of an object strongly depends on its temperature. So 1,000,000 degrees object just glows very, very bright. Now, the light emission from the gas particles in the accretion disk span from the X-ray to the infrared, and it peaks in the UV. But there are also other components of an AGN, or of a quasar, that you can see in different parts of the electromagnetic spectrum. So now we're going to talk about the different components of a quasar. At the center you have the black hole, and around that is the accretion disk. The black hole obviously doesn't radiate at any wavelength. In the accretion disk, like I said, spans X-rays, peaks in the UV, and into the optical and IR. Then outside that, you have the donut, the delicious Krispy Kreme donut of a quasar, which is actually the dusty torus, which is a cool gas. It radiates in the infrared. Above the accretion disk, you have these black dots, part of the broadline region, which includes ionized gas that's not as hot as the accretion disk, but it's still quite hot and rapidly swirling around, and it creates broad emission lines in the UV and the optical. Above the broad emission line, you have the narrow line region, which has cooler gas, and it's not moving as fast, so it has narrow emission lines. And finally, you have a jet of the relativistic electrons producing radio waves and X-rays. So why am I talking about the components of an AGN and their different observational signatures? That's because there are other types of objects that we observe that have a combination of these signatures. And that's quite confusing to astronomers, because how can you have, let's say, maybe just the narrow lines of a quasar, but not, let's say, the radio jet? And so I have a couple examples of different types of objects. I have 3 examples. One is a Seyfert galaxy. So a Seyfert galaxy is like a quasar because it will have broad emission lines in the optical, but it looks like a galaxy and may not have a radio detection. And like I said, quasars often were discovered by their radio detection. Then you have blazars. Blazars are interesting because they have the power law continuum like a quasar, but has no broad or narrow emission lines on top of the continuum. So they're quite strange. And then you have dragons. Yeah. And yeah, Dragon Queen Danny, yeah. But no, not that type of dragon, this type of dragon. It's a galaxy with 2 large radio lobes, or jets, on either side. But it doesn't really look like an AGN. So, astronomers came along, tried to figure this out, and they realized that actually all of these objects have the same central source, but we are just seeing different parts of it. This is called the unification model of active galactic nuclei. And so quasars are just one type of active galactic nuclei. And the type of object that you see depends on the orientation of your view compared to the rotation disk. And so this is another diagram of the components of an AGN, but now with eyeballs around the outside. And the eyeballs and then the labels next to the eyeball show you what type of object you would see from that angle. So quasars also go by the name of QSOs. So the things I was talking about earlier, you see from an angle. Blazars, which are here, you're actually looking down the jet of the quasar. And the jet basically blocks the view of the accretion disk, and so you don't see the broad emission lines. And finally, if you see it from the edge, the whole accretion disk could be blocked by the dusty torus, leaving maybe just the view of the jets to either side. Here's a movie showing that from this view you would see a quasar, broad emission lines, power law continuum. But if you were looking from the edge, the dusty torus can block out that view entirely. For the last part of the talk, I want to talk about how quasars are used as a tool by astronomers to study the universe. And so essentially, you can use quasars to study the gas in between quasars and our instruments. What happens is, as the quasar light is emitted, it becomes redshifted, and that light can interact with the gas through absorption. The gas will absorb lines and take a slice out of the quasar spectrum, which is shown here. And then as the light travels further, it will be redshifted more, and then gas of a similar type will take a chunk out at that point in the spectrum, and so forth. That leads to absorption line spectra on top of in the continuum and the broad emission lines of quasars. Here's a movie of that. I think we can do it. There's a lot going on here. I hear you guys are really smart, so I'm not worried. So at the top we have what's going to be a movie. This is going to be like the quasar, and there's going to be a light coming out. That's going to be the photons. And then the photons are going to travel through clouds, and we're going to move along with the photons. It's actually going to pass through a galaxy, and then it's going to get to the telescope. And at the same time, while the movie's running, this down here will show the spectrum of the photons at that particular time. So right now, you see the spectrum of the quasar as you would see it if you were right next to the quasar. Then I'll hit play, and it will move, and you will see absorption lines appear through the spectrum. So let's give it a go. So the most popular absorption line is from hydrogen. Hydrogen, they call it the Lyman alpha line. And this creates what's called the Lyman alpha forest. And yeah, the light goes through the clouds and are making more lines. So if you study these individual lines and their profiles, you can actually measure the amount of gas and the type of gas along the line of sight throughout the universe for light years. And I'll just go back to when there was a galaxy. This light can go through galaxies, and galaxies have a lot of gas, so they create much larger features. And so with this technique, astronomers can study not only gas between our galaxies, but in other galaxies, and also gas in our own galaxies. So one of the projects I did as an undergrad was study high velocity clouds, which are interesting because they're clouds in our own Milky Way that are shooting out of the disk, and you can study those to understand properties of supernova feedback and metal enrichment in the galaxies. So with that, now you all know what a quasar is. you know, gotta play my little movie. Yeah, you know that they are part of the AGN family, and you know how quasars are a tool for astronomers. Thanks.
Thank you, Active Galactic Nuclei guy. So we have some time for questions. Actually, first we have a Twitter question from Kim Moreland asking, so quasars are used to, so they're black holes at the center of quasars. Are all black holes at the center of quasars?
Yes.
Wait, opposite question. Do all, do all black holes,
So,
are they surrounded
the
by?
way I interpret it was, do all quasars have black holes? And that's yes. But no, you can find black holes at the center of other objects. Or, for instance, all galaxies have supermassive black holes, but not all galaxies have quasars.
Mm-hmm. Yes, sir, right there.
What causes the jet to shoot out from the rotational axis?
Yeah, so that's, so no one really knows.
Repeating the question, what causes the jet to shoot out of the quasar?
Thank you. It's unclear, but essentially there are strong magnetic fields that happen because you have charged particles essentially moving, and when you have charged particles moving, you get magnetic fields, and then the magnetic fields twist and form collimated jets, and some gas gets swept up in there and can get shot into space. Yes. Sorry.
Yeah, it's fine.
Quasars are useful for exploring what is between the observer, us, and the quasar.
Yeah.
Why is that? Is it because of the range of spectrum that the quasar emits, or could another object be just as useful to study what is between us, the observer, and it?
Yeah, so the question is, we use quasars to study the gas between distant quasars and us. Can you use other objects to study gas between that object and us? And the answer is yes. Anything that creates a nice broad spectrum that you can characterize easily, you can measure the features of the absorption in those spectra. Quasars are nice because they're quite smooth. And remember the blazar is just a smooth power law. So all you have to do is fit a line to that, and then you go and you look at the individual lines. But yeah, you could do that with any broad spectrum object.
Yes, sir.
Do quasars exist in the galaxies, or are they like larger than galaxies?
Yeah, good question. So the question is, are quasars in galaxies, or are they like as large as the galaxies or larger? The answer is they are at the very center. So quasars are about the size of the solar system. And as you know, our solar system is just inside the disk of the Milky Way, so much smaller.
Yes, sir, over there with the sunglasses on your head.
Is the jet something that you could feel that would push you? Like, is the jet, what's the jet made of? Is it going to push you around? Do you fly in front of the jet so you can harness, or do you wait?
Right. Yeah, so the question is, what is in the jet? So the jet is full of relativistic charged particles. So if you were nearby and you were in the jet, it would fry you. You'd get destroyed.
Could you put a mirror behind it and have it push you?
Sure. Yeah. Could you be pushed by it? Yeah. So if you had a strong enough material that wouldn't get fried by super energetic particles, then yeah, why not? Yeah.
Uh-oh, don't give him any ideas. Last question on the staircase.
The question is, do we know how many there are in the universe? I mean, we have a good idea. They're not as common as all galaxies. Like I said, not all galaxies have supermassive black holes, but not all galaxies have quasars. And so, yeah, just like we study galaxies, as Casey showed. People are very interested in the evolution of quasars over time, and so yeah, someone has a good handle on how many quasars there are.
You can ask him at intermission. So let's thank Active Galactic Nuclei again.